Hi everyone, welcome to Cram for Chem. In this video, we'll talk about molecular geometry, which is the shapes of molecules. We'll also go over polarity of molecules, hybridization, and sigma and pi bonds. Molecular geometry is built on the valence shell electron pair repulsion theory, or VSEPR theory. Despite how long and complicated the name sounds, it's actually a very simple concept. Electron domains repel each other, leading to predictable molecular geometries. Electron domains are regions with electrons, including lone pairs, single bonds, double bonds, and triple bonds. All of these count as one electron domain. What you'll see in the next couple of models is that electron domains want to be as far apart from each other as possible. The models coming up are very commonly seen in chemistry, so it's useful to remember how they look, what the bond angles are, and what the geometry name is. Here's a molecule with one central atom and two electron domains around it. The two domains repel each other, so to get as far away from each other as possible, any atom with two domains will have a 180-degree bond angle. This molecular geometry is called linear. Here's a molecule with three electron domains. It has a bond angle of 120 degrees, and this geometry is called trigonal planar. These are all molecules with four electron domains. Regardless of whether the domains are bonded atoms or if there's lone pairs involved, the general shape of these molecules is the same, and the bond angle for all of them is about 109.5 degrees. This first geometry is tetrahedral, the second is trigonal pyramidal because it is a pyramid shape, and the last one is called bent. There's a bit more I want to explain about these diagrams. Take a look at the different ways of drawing chemical bonds. There's normal lines, dashes, and wedges. This is to give us an idea of what these molecules look like in 3D. If you see a normal line, that means the bond is lying in the plane of the page. If you see a dash, that means the bond is going into the page. If there's a wedge, that means the bond is coming out of the page. Imagine poking a pencil through a piece of paper. The part of the pencil behind the page would be a dashed bond, and the part of the pencil pointing at you from the front of the page would be a wedge. Now let's talk about bonded atoms versus lone pairs. Although these three molecules all have four electron domains, lone pairs do change the bond angles a little bit. Take a look at the third structure with the two lone pairs. This is the structure for water. Lone pairs repel electron domains a little bit more than bonds, so they will push the bonds away. This shrinks the bond angle a little bit. As a result, water's bond angle is 104.5 degrees, just a little smaller than 109.5 degrees. Here we have a molecule with five domains. There are two different bond angles in this structure. There's a 90-degree angle here and here in the plane of the page, but if you look at this molecule from the top, there's a 120-degree angle between the three red atoms. This geometry is called trigonal bipyramidal. Finally, if you have a molecule with six domains, it will have a bond angle of 90 degrees. If all the domains are bonded atoms, then the geometry is called octahedral. If there are two lone pairs, it is square planar. The molecular geometry affects a molecule's polarity. Molecules are polar if they are not symmetrical. Polarity means the molecule has one side that is partially positive and one side that's partially negative. Take water, for example. Water is not a symmetrical molecule. There's a partial negative on the oxygen because oxygen is more electronegative than hydrogen, and also because that's where the lone pairs are. There's a partial positive on the hydrogen side. On the other hand, carbon dioxide is a symmetrical molecule. Oxygen is more electronegative than carbon, so oxygen has a stronger pull on the electrons, but the pull on both sides cancel out, so carbon dioxide's symmetrical geometry makes it nonpolar. Now let's get into hybridization and bond types. Hybridization happens when atoms form electron domains. They mix their s and p orbitals so that the domains are equivalent. To figure out the hybridization on an atom, the trick is to count the domains around the atom. The first orbital to contribute to hybridization is s. All others are p. The number of s and p orbitals that contribute to hybridization is the same number as the final number of electron domains. Here's an example. In this H2 molecule, this hydrogen only has one domain, which is the bond. The first orbital to contribute to domains is s, so this hydrogen is not hybridized. It's just using its s orbital electrons to make the bond. Same thing with the other hydrogen. Now let's look at this molecule. This carbon has two domains. The first orbital type to contribute to domains is s, and the others are p, so we say that this carbon is sp hybridized. This nitrogen also has two domains. The first orbital to contribute is s, and the rest are p, so this is also sp hybridized. Same thing with this carbon and carbon dioxide. It has two domains, and it is sp hybridized. All atoms with two domains are sp hybridized. Now let's look at three domains, like this oxygen and carbon dioxide. The first orbital to contribute to domains is s, and the rest are p, so this oxygen is sp2 hybridized. Same thing with this other oxygen. Take a look at the carbon in formaldehyde. It has three domains. First orbital to contribute is s, and the rest are p, so it is also sp2 hybridized. All atoms with three domains are sp2 hybridized. Finally, let's look at four domains, like the carbon here. By now you probably know the pattern. First orbital to contribute is s, and the rest are p. This carbon is sp3 hybridized. This oxygen also has four domains. It is sp3 hybridized. All atoms with four domains are sp3 hybridized. The last thing I want to talk about in this video is bond types. Sigma bonds are stabbing bonds where orbitals meet head-on. Pi bonds are parallel bonds where p orbitals line up lengthwise. When you have bonds and you want to know what the bond types are, the concept is similar to hybridization. The first bond that forms is sigma and the rest are pi. If you have single bonds, that's only one bond, so it's sigma. If you have multiple bonds, the first is sigma and the rest are pi. So if you have a double bond, you have one sigma and one pi bond. If you have a triple bond, you have one sigma and two pi bonds. I hope this video was helpful. Thank you for watching, and I'll see you next time.